All right, so thank you all for coming. So today I'm going to be talking about quantum entanglement. So specifically, I'll talk about the following. So just the basic definition of entanglement. We're going to talk about Schmidt decompositions and how they can be used to measure entanglement for pure states. We're going to talk about what happens when we try to do the same thing with mixed states. Turns out you can't measure entanglement easily with mixed states. We'll talk about the Schrödinger-HJW theorem, which addresses the issue in number 3. We'll talk about entanglement measures and the convex roof instruction. And then lastly, we'll talk about approximating optimal pure state ensembles, and we'll look at a quantum algorithm for approximating. Okay, so first things first. So the general setting we'll be looking at is two finite dimensional Hilbert spaces A and B. So I'll just denote that as H in general. So all of the states that we consider are A and B, so I'll just kind of use those A and B later in the talk as we can continue. And so let's look at what product states are. So if I have some pure state on my Hilbert space, it is a product state if it is equal to some alpha tensor beta, where alpha lives in A and beta lives in B. Okay, and we say that if C is not a product state, then it's entangled. So if I can't write my state as a simple product like that, then we say that the state is entangled. Okay, so for density operators, it's a little bit more complicated, and we call them separable instead of product states. We say that a density operator is separable if it can be written as a convex sum of product states, where rho j and sigma j are densities on A and B respectively. And note here it's a convex combination because these some of the lambda j's goes to 1 there. Okay, so if I give you some state rho, how do you know whether or not it is entangled? Or not rho, but any state. So one way you can do this is using Schmidt decomposition of a state. So what that is, so first let's write our state on our Hilbert space H as a sum over the coordinates I and j. We have these Cij, and this is a pure state. And what we do is we use the natural isomorphism with A tensor B and the linear operators from A to B. And this isomorphism essentially just makes that ket J on the right-hand side of the tensor into a broad J. So it just turns this thing into a matrix and the tensor disappears. So this new element in LAB is just the operator C, and the entries are the Cij, where the Cij are just those coordinates right there. So what we can then do is, since now we have a matrix, we can take the singular value decomposition of C. And that gives us our singular values sigma j, which are greater than or equal to 0, and those beta j are orthonormal vectors. Okay, and the singular values sigma j, these are called the Schmidt coefficients of C. Okay, so you may know that okay, so now undoing the isomorphism, we rewrite our state C as the sum over sigma j, alpha j, beta j. And you may know that the length of the Schmidt decomposition, the singular value decomposition is unique. So if we only have one singular value, then the C is a product state. So that means that we don't even have a sum, we just have an alpha tensor beta. But if we end up with more than one of these singular values, then that means that our state is entangled. So that's a simple way we can do that for pure states. Okay, but what about mixed states? So if I give you a density operator, will something similar work? And maybe a natural question would be, can we use something like the spectral decomposition of a state? So what if I give you this state, a rho, where it's just 1/2, and then the state is 0, 0 on one space, or on the space, and then it's 1/2 probability 1, 1 on the space. So what if I try to measure the entanglement of this? Well, if I look at this thing, so if I just looked at the vectors here, neither one of them is entangled. So whenever you observe your state, it's going to look like either a 0, 0 or a 1, 1. So only one of those will appear. However, you can also write it this way. So if you just write out these Bell states right here, you notice some cancellations, and it actually turns out to be the same thing as in 4. However, we just wrote our rho as a linear combination of entangled states. So the Bell state C plus and C minus, those are both maximally entangled. So here what happens is if an observer tries to measure that density operator in the Z basis, then the state you observe will always be a product state. You'll only ever observe 0, 0 or 1, 1, never any superposition of the two. So that would lead the observer to think that the state is separable. However, if the observer decided to measure the state with respect to the Bell basis, then you would always measure one of the Bell states, either psi plus or psi minus. So that would lead the observer to think that the state is indeed entangled, which would be incorrect here. Okay, since both expressions are indeed spectral decompositions, because both are orthonormal decompositions of rho there with the same spectral values, that shows that using the spectral decomposition is actually a bad way of using entanglement. And in fact, there's actually uncountably many infinite decompositions of such a state, and all of them each have various measures of entanglement. And we'll talk about what that means in a second. And these decompositions are often referred to as pure state ensembles, and they're related by the following theorem. So if I give you a density operator rho and I write it out as an ensemble like this with pj's and phj's, and these don't have to be orthonormal phj's either. They can be more than the rank of rho. And I give you some convex coefficients pj. What we can do is purify it. So define this state psi, where I basically just tack on a ket j to the phi j for each j. So this is now a pure state, and I've attached an ancilla space. Now what I can do is apply a unitary on my ancilla space. So not the A tensor B, but just on the ancilla that I did. And this will also be a purification of rho. And that follows from this computation right here. So if you trace away that ancilla space with the unitaries there, you can use the cyclicity of the partial trace in the space that you trace away to get back to the trace W psi psi. But if you also keep the unitaries there, you can actually end up with a different decomposition. So number 7, so equation 7 here, and where these gamma j are defined as follows. So first we define these gamma tilde, where we sum over some of the entries of the unitary operator, and we have those pk's in there from earlier. And we define the probabilities. Qj is just the norm squared of those gamma tildes. Next, we define the gamma j's as this. So it's the normalized version of the gamma tildes. However, like I said, this trace rho with the unitaries is equal to the trace, there should be a trace W right there, my bad, is equal to my rho. So what this means is that the sum over the pj phi is actually equal to the sum over the qj with the gamma j. So these two have to be equal. And since before we defined the sum of the pj phi as rho, that means that my sum with the qj gamma j is also equal to rho. So we found ourselves another pure state ensemble. Okay, so since there's infinitely many pure state ensembles for a general mixed state rho, how do we determine whether or not it's separable? Okay, well, one idea is to define a function that returns 0 when I give it a state that is separable, and return something that should be greater than 0, my bad, when a state is entangled. So it returns 0 if it's separable, and something non-zero when it's entangled. And such a function that does that is called an entanglement measure, but it has a couple more properties, which we won't discuss in very much detail here. But the general idea is the following. So let mu be a function from the density operators on A tensor B to the positive real numbers. We call mu an entanglement measure if the following 3 properties hold. So mu of rho is 0, if and only if rho is separable. We call that faithfulness. If I take an LOCC channel of rho, then the entanglement of the L of rho is less than or equal to the entanglement of rho. So I'm not going to really go into LOCC channels in detail here. You could spend a couple lectures going over those, but the general idea is that for those channels, you have 2 spaces A and B. One person is doing operations on their side, the other person's doing operations on their side, and they're not correlated. So they're local operations, and they can talk to each other about their measurements, so classical communication, so LOCC. So that's the gist of that. And then the mu should also be invariant under local unitaries. So if each party applies unitaries to their piece of the state, then it shouldn't change the amount of entanglement there. Okay, so how do you construct such a function? So those are nice properties and all, but how do you figure out how to define such a thing? Well, a typical construction is the following. So you start with a concave function f, and this is on the density operators of just A. It could also be on the density operators of B. It's kind of assumed that it works for both spaces. And it should go to the non-negative real numbers. and it should depend only on the non-zero spectrum of a given density. And what you do then is you define your entanglement measure mu for pure states by saying mu of psi is equal to f of the trace b of the psi psi. You could also trace away the a instead, so it doesn't matter which one you choose. I just chose the first one for simplicity here. Okay, and when you do that, you end up with an entanglement measure. So let's look at some examples of these. One is the entanglement entropy, so probably the most popular one. And here you define your f of rho to be the negative trace of rho log rho. So I give you a density, you just plug it in, you take the partial trace, and you plug it into this function here. So the entanglement entropy of E would just be f of the trace B psi psi. Okay, so that's probably the most common one. Another one is called the Meyer-Wallach measure. And here we define our G of rho as 1 minus trace rho squared. And then we define this Q of C as 2 times that. So it's just a normalization factor. So its maximum value is 1. And then I plug in the trace B of psi psi again. Okay, so these are two of the most common ones you'll see. So there's other measures of entanglement and some more complicated ones, but we won't go into those. But notice here, I only defined these for pure states. So what happens when I do mixed states again? Well, we get the same issue because you end up with all of these different ensembles of my state. So we saw earlier there's infinitely many different ones. So when I try to do this f of trace b sigma for each different ensemble, I'm going to get a different answer out of that mu. So it doesn't make quite as much sense to do this with densities either. So that's where this comes in. So useful quantity to compute would be maybe the minimum amount of entanglement present among all possible ensembles. So instead of looking at just one, we compare every single ensemble of a state rho, and we look at the minimum amount of entanglement. Because if you wanted to use that entanglement as a resource, if you know that sometimes you'll get 0 entanglement, well, that might not be a good resource to use for your entanglement. So we'll look at the minimum of it. So in order to do that, we have to define the set of all pure state ensembles, and we're going to call that CD of rho. And it's defined by this complicated expression in equation 8 here. So we take all convex coefficients, the lambda I, and all pure states Ci, and we want them to sum to rho. So if I take the sum, lambda I, Ci, these things should sum to rho. Okay, so these are all the convex decompositions of rho. And now I can define my entanglement of rho as the following. So for any density operator rho, I define mu of rho by the infimum over that convex decompositions of rho, where I take the entanglement of the psi and multiply by the convex coefficient, and then add it all together. So it's kind of like the expected entanglement out of an ensemble. This is one way to think about it. And then we minimize that expected entanglement. Okay, so this construction is often called the convex roof construction. And moreover, any ensemble that I give you, so lambda I Ci, for which the infimum is achieved, is called an optimal pure state ensemble. Okay, so one might ask, well, how do we know that we can even find a minimum here? Well, it turns out for a lot of the mu that we care about, this happens to be the case. So George Androulakis and I, we proved the following theorem. We said that if H is a finite dimensional Hilbert space and mu is a function from H to the non-negative reals, if mu is norm continuous on the Hilbert space, then the infimum is achieved for all density operators rho on H. So that means that we know if our mu is continuous, then we'll always get a minimum there. So we can always find a minimum amount of entanglement. But you might ask, well, is continuity too big of an assumption for our states? Well, it turns out that LOCC monotonicity is dependent on the existence of these optimal pure state ensembles. So it's not restrictive in practice to actually impose continuity on our entanglement measures, because for the ones we already use, for instance, the entanglement entropy or the Meyer-Wallach, they're already continuous. So it doesn't matter if we impose continuity on our entanglement measures. All right, so we know that the optimal pure state ensembles must exist for any of the mu that we care about. So how do you compute them? So that sounds kind of like a challenge because we're minimizing over a really complicated set, right? Well, there are a couple of algorithms that do this, and all of them do the following thing. So since all of these ensembles are related by unitaries, you can transform that infimum over the convex ensembles of rho into an infimum over the unitary group. So this happens to be a compact manifold. So if your function is continuous and your manifold's compact, then you know you're going to get a minimum there. So your function will achieve its optimal points. So, and the general process is the following. So first you start with an initial ensemble. So a lot of the algorithms just use the spectral decomposition. So that would be one possibility. And that's not really too hard of a question to ask, because if you want to find the entanglement of an ensemble, you kind of already know what states you're looking at in the ensemble anyway. Okay, so you start with your ensemble. And then what you do is you define H of U to be that entanglement at that unitary. So kind of the expected entanglement at that certain unitary where you've used that Schrödinger-HJW theorem to obtain a different ensemble there. And then next, you minimize H over the unitaries. Okay, so that sounds simple enough, but it turns out that requires actually a lot of geometry. So all these algorithms are classical, and the minimization relies on the geometry of the unitary group. Okay, well, I'm not good at geometry, and one might ask, is there a better way to do this? Because we're studying a very non-classical thing. So we're studying entanglement, so would there be a quantum approach to doing this? Well, it turns out that Schrödinger-HJW theorem told us yes. And we're going to discuss that algorithm now. So if we fix an ensemble again, so we start out the same way, you have your ensemble here. And then you prepare that purification of rho. You prepare that C, where it's the sum over lambda I, vi tensor I. Okay, so you prepared this state. And then what you do is you parametrize the unitaries somehow. And we'll discuss that parametrization in a second. And what you do is you apply identity on the phis, but you apply the unitary to the ket i's over there. Okay. And then you measure your state. And so we'll discuss the measurements in a second, but the general idea of the algorithm is that once you measure, you get some results and you update your theta in the direction of u. So your unitaries are parametrized by some vector theta there. And then you go back to step 2 and you iterate as necessary. So you can use any kind of optimization algorithm, just pick your favorite one. Okay, so let's talk about those u thetas right quick. So the u thetas that we use, they're of the form, so they're products of exponentials of Hermitians and then times a wj, where these wj's are independent of theta. So usually in practice, they look like some kind of controls between the other qubits. And the HJs are picked randomly. And the theta J's are also picked randomly uniformly, so that our initial guess, u theta 0, is assumed to be Haar random. Okay, so these unitaries are considered, called random parametrized quantum circuits. And this is one of the things that the Google quantum group considered in a lot of their experiments. Okay, so now let's look at the measurements right quick. So what happened when we measure? So when we measure the oscillospace, we observe the state I with probability Qi. And this Qi, so that's the probability from earlier with the HJW theorem. And it's that the gamma tilde, where we define the gamma tilde as this vector right here. Moreover, since of how we define the psi, whenever we measure the state I, that means that we have forced the other qubit into the state gamma I. So now we know that we are in the state gamma I tensor I. And then what you do is you can use your measurements to compute that function h of u of theta and its derivatives. So in general, what you can do, you can use just a finite difference approach. It seems to work fine, and use something like stochastic descent. So that when you do the finite difference approach, you can plug in like the theta plus h in a certain direction of theta, plug that back into your quantum circuit. So you're offloading some of that computation back to the quantum computer. And then you take your, you take your derivatives and you compute that and update your theta again. So let's look at the circuit. It is surprisingly simple. So you start with some zeros and you prepare your state C from those zeros. And then you apply the U and you measure. That's really all there is. The rest of the algorithm is just plugging things back in to get your derivative and optimization. So you can offload that to the classical computer now. So what are the drawbacks of this? So if you have a very large state with a lot of qubits, well, that could be intractable right now because the quantum computers we have don't have a lot of qubits. So if you want something more than just 2 or 3 qubits for your state, then you're going to have a hard time actually implementing the algorithm. Because you need, so if we look back at the circuit right quick, you need enough qubits for your space A tensor B, and you need enough qubits for your ancilla space. You have to have as many qubits, or almost as many qubits as your as the length of the ensemble. And another issue is that numerical results suggest that we have barren plateaus for a lot of the common entanglement measures. So a lot of the coding we've done, it looks like we have barren plateaus for the entanglement entropy and for the Meyer-Wallich measure. We're currently trying to prove that, but just numerically, it seems like we're going to have that issue. But what about the benefits? So we can use that quantum computer as an oracle for the ensembles, and that greatly simplifies the computations. Because if you look at the algorithms and the papers that I linked for the classical algorithms, they're actually really complicated. There's a lot of stuff that you have to do to actually figure out the function in terms of Q. And another benefit is that you can actually implement some of the entanglement measures on a quantum computer. So the Meyer-Wallich, for example, so instead of actually doing your computation off of the quantum computer, you could perform that first circuit and then do the circuit that does the Meyer-Wallich measure, and then get your result that way. And then you can do that a couple of times to get your derivatives too. So you've put more of the computation onto the quantum computer, and you really only have to do like something like stochastic descent offline on the classical computer. Okay. So that was actually really fast, and I finished the presentation there. So are there any questions?
So I have a it's just sort of a, I don't know, maybe a conceptual question. So when you do this sort of descent algorithm, and you compute an approximation of the derivative, and you step down. Is there anything? Do you know? I mean, these manifolds, the U sub n, the unitary groups, are they smooth enough that you can do something like Newton's method and maybe get a faster convergence?
I think so. So that's one of the classical algorithms that I showed. So let me go back to that. They actually do something called a conjugate gradient method on the manifold. I don't actually know what that means fully. So I think so, yes.
Okay. Oh, okay. All right.
Let's see. Yeah, here we go. So yeah, there's some links in one of these slides that show the paper, and you can see what they do. But they do something similar to Newton's method, I believe, but more complicated.
All right. Thanks.
Mm-hmm. All right. Any other questions?
So does the choice of the optimization algorithm affect the efficacy of this algorithm in any?
I don't know that it affects the application. So I think however you choose to optimize, that's fine. You just might run into some issues with certain optimization algorithms being slower or faster. So for instance, the stochastic gradient descent is really fast. So for some states, you can get the entanglement entropy to converge in just 1 or 2 iterations. So it's like that. But also for some states, you get stuck in these barren plateaus where you never converge. But I think that more sophisticated optimization algorithms will avoid the barren plateaus, but they might take a week to run. So you get the same result, but somewhat faster, or sometimes it doesn't converge.
Okay, thank you.
Mm-hmm. All right, any other questions?
Could you share your slides with people? Maybe a link if you've got it, if you don't mind.
Yeah.
It's got some links to the archive. It would be nice to have.
I can send that afterwards.
Thanks.
Mm-hmm. Okay. Anybody else?
Okay.
Very good talk, Ryan. Thank you.
Yes.
Thank you. All right.
Yes, thank you very much.
So short there. I'll work on taking up more of your time next time.
Right.
Problem I usually have. I fly through my lessons and presentations. All right, so thank y'all for coming. I can go ahead and stop recording.
Right. Thank you, Ryan.
Yeah, thank you.
Thank you.